Hi everyone, welcome to another video on using Excel. Today's video is a continuation of the previous video on normal data distribution and the z-scores in Excel. This will also be our segue to an upcoming video on cumulative data distribution function in Excel. We'll begin with a quick recap of what is a z-score. A z-score is defined as the difference between the data point and the mean divided by the standard deviation. The net effect of this calculation is that it gives us how far or how close a data point is to the mean of a distribution, or to be more precise, of a normal data distribution in terms of standard deviation. If the data point is to the right of the mean, it shows up with a plus sign. If the data point is on the left of the mean, then the z-score has a negative sign. For example, when we say that the z-score of a data point is plus 2.5, it means that it is 2.5 standard deviations away from the mean and it is to the right hand side of the mean. Likewise, if the z-score of a data point is minus 1.7, it means that it is 1.7 standard deviations away from the mean and it lies to the left of the mean or left of the average. We looked at the normal data distribution in the past. We know it is often also known as a bell-shaped curve. Well, that's not strictly speaking true, but that's common nomenclature that you'll hear in business or in text also. The other known name of a normal distribution is a Gaussian distribution as well. We know that a normal distribution is symmetrical about the vertical axis, and two important facets of a normal distribution that help us a lot in terms of calculations is one, the 68, 95, 99 rule that we looked at last time. In brief, what this rule says is that for any normal data distribution, 68% of the data lies between plus 1 and minus 1 standard deviations. 95% of the data approximately lies between plus 2 and minus 2 standard deviations. And then 99.7% of the data lies between plus and minus 3 standard deviations. Also remember that any normal distribution can be defined completely by 2 and 2 numbers alone, which is the mean and the standard deviation. There is a very complex formula, as you can see on the screen. However, we'll not use that today. Often with normal data distribution, what is used are the actual relevant representations of z-scores. So for instance, if you see on the left hand side, you have a graph giving data points in which the mean is at 60 and the standard deviation is at 10. And that's why you see the data distribution is spread all the way from 30 till 90. The equivalent z-scores are given on the right hand side. This is just again for conceptual clarity. You will see that the mean value of 60 is now reduced to a z-score of 0. You'll also see that the maximum value of 90 has a z-score of 3, while the minimum value of 30 has a z-score of minus 3. All of this is a function of the formula that we looked at, which is z-score will be defined as the data point minus mean divided by standard deviation. Also bear in mind, it's very important that the sign of the z-score tells you whether the data point is to the left or to the right. Now, z-scores are often used in conjunction, in collaboration with something known as a z-score table. A z-score table is nothing but a tabular format which helps us get the percentage of data points of a distribution that lie to the left or that are below a given data point in a normal data distribution. So there are several applications of a z-score table. What I've done here is split them up into two separate parts. So the first application area is when you have a z-score and you're trying to find the area or the percentage of data points, the area of the curve of the normal distribution or the percentage of data points. So here you can use a z-score table. Given the fact that you already have a z-score, The other application, as you can see, is mentioned on the right hand side is the reverse application, which is given the percentage of data points, or given the area of a normal distribution, if you want to get the z-score. This is something that we'll cover in a future video. It has a lot of applications, the understanding of this, especially towards the use of z-scores when you want to use z-scores for critical region or critical point testing in relation to hypothesis tests. That's where this will be useful. And this will be covered again in a different video. For today, we are going to first try and understand the applications that we have on the left hand side, which is the area below the z-score. So whenever we have a z-score and we want to understand the percentage of data that lies below or that is less than that data point, we will use the first concept. In some cases, you might also need to find the area above the z-score, which is nothing but the percentage of data points of a data distribution that lie above a given data point. There are also known applications to find area between two z-scores and areas which are outside z-scores. When we say outside, what we mean is those data points which are above the max point of the data distribution, and basically those points which are below a given score. So basically above a given score and below a given score. So I think this will be much clearer if we were to look at some examples. We'll start at the first example, which is area below the z-score. So this is a concrete example of a problem that we're trying to understand and try to solve. So the question here says that if there are 100 students at a university that took an exam, and the mean score was 60 marks, the standard deviation was 10 marks. If a student scored 78 marks in the exam, what is his or her percentile score? Assume a normal distribution, which is the key assumption here is that our data is normally distributed, as covered in the previous video, using the concept that almost the entire distribution or 99.7% of the data lies between -3 and +3 standard deviations. We can first of all derive the minimum or the least point of the data distribution, which is mean minus 3 times standard deviation. And that is what leads us to the starting point of this distribution. You can observe by the formula in the formula bar, and you can see how did we arrive at this number. So the 60 here in this formula is the mean. Minus 3 times the standard deviation of 10 gives us the minimum point of the data distribution. And from there onwards, remember that our maximum point is going to be nothing but, it will be the mean, which is 60, plus 3 times the standard deviation, in this case is going to be 90. So you will see that in this distribution, we have taken data all the way from 30 to 90. There we are. And then for each of these supposed data points, remember these are not the actual scores. This is just to arrive at what the distribution would look like. So if the score is 30 on a distribution, the z-score is -3. Remember the nomenclature, minus means that the data point is towards the left of the mean. We know that the mean is 60, so it does make sense. The 30 will be towards the left of the mean. The -3 tells us how far away is the data point 30 from the mean being 60. Now this here is the probability calculation. So what is this? So if you recall from previous video when we were trying to understand the Norm.Dist function within Excel. So the Norm.Dist or the norm distribution function within Excel, what it does is it takes a certain data point value, it takes the mean, it takes the standard deviation, and if you use the last parameter as false, it gives us the probability data distribution number or the probability. If you were to use the value true in this function, so instead of false, if the last parameter was true, then that would give us the cumulative distribution, which is again something that we have reserved for an upcoming video. For now, bear in mind that if you use a data point along with the mean, the standard deviation, and the final parameter is kept as false, it will help us generate the probability distribution for that number. And now if we plot the probability distribution for all of these data points starting from 30, which is the lowest point on this, all the way till 90, then you can see this is how the distribution looks like on the right hand side under standard normal distribution. You'll see the center point is at 0 and it stretches all the way from -3 to +3. So now back to the question that we were at. So if there were 100 students at university who took an exam, the mean score was 60 marks and the standard deviation was 10 marks. If a student scored 78 marks in the exam, what is his or her percentile score? Assume a normal distribution. Now to address this, what we'll have to first understand is the student who scored 78 marks. What was the z-score of 78 marks? So here, if you scroll down the table in which we have calculated the z-score and the probability value and go all the way down to, let's say, the score of 78. You'll see that for 78, the z-score that we have calculated out here is 1.8. It is 1.8. So given that the z-score is 1.8, this is where the z-table will be of a lot of use to us. So let's go ahead and see what is the corresponding value in the z-table for 1.8. So if you go here, we go to the z-table screen. The table on the left is of negative values, but what we are interested in is positive 1.8. So let's look at this. So here, if you take a look at 1.8, you can see that z-score of 1.8 is 0.96407, right? So it is 0.96407. So what does this mean? What is the meaning of this? What this means is that 96.40%, 96.40%, or rather 407%, which rounds off to 41 roughly, percent of the data lies to the left or lies below the z-score of 1.8. The other way of looking at this is that 96.41% of the data points in this normal data distribution would lie to the left of the score, which is 78. Now let's look at this visually to understand this better. So going back to our normal distribution graph here, if we were to plot 78 marks, now remember 78 marks corresponds to 1.8 or plus 1.8 standard deviations. If you were to look at it on our graph, we will see that the 78 marks or the 1.8 data distribution will lie somewhere here. Right? So this, as you can see right here, is 1.8. We'll just mark this one in red for easier visibility. So this red colored column right here represents 78 marks or 1.8 z-scores. And whatever you see right now to the left of this red colored column, which is all this brown colored section, all the way from -3 all the way to below 1.8, is basically the number that the z-score table is giving us. So remember that z-score table had given us 96.41. That is what it means. In other words, whenever you look at a z-score table, the value that it gives to you for a corresponding z-score is nothing but the percentage of data points which lie to the left of the corresponding z-score. So we now know that 96.41% of the data lies left of 1.8 or left of 78 marks. That is the actual interpretation of that. We also know that the complete area of this normal standard distribution is 1. So we know that if 96.41 lies below that data point, then what is the value that lies above? that data point. This is the corresponding value, which is 3.59%. So now we understand that the brown colored section is 96.41 and the blue colored section towards the end is your 3.59%. So this is how we can calculate the percentage data distribution which is less than a given number. So going back to that question, the mean score which was 60 marks, standard deviation was 10. If a student scored 78, what is his or her percentile score? Remember, the percentile score is nothing but the percentage of students who would have scored below the student, which we now know by the graph is roughly 96.41%. So that would be the percentile score for the student. Now, as stated before, that not only can you use the z-scores for calculating the area of a standard normal graph, which is below a certain data point, or in other words, a percentage of data points below a given data point, but you can also calculate what is above the data point, which is nothing but the reverse. So the same question that we just looked at in the previous example is now turned on its head, and here what's being asked for is what is the percentage of students who have scored greater than 78 marks on the exam. So the same logic, if you were to calculate the z-score of 78 marks, you will realize that the z-score of 78 marks comes to 1.8. As you can see here, it is 1.8. For 1.8, if you go to the z-score table, it is 0.96407 as mentioned there, basis which you can now understand that the dividing point on this data distribution is again going to be 1.8. So in this example, we are being asked to calculate the percentage of data points above. So whatever you see in brown color on this normal standard distribution graph is our required answer. So the required answer is 3.59. How do we arrive at this? Again, remember, for 1.8 z-score, the percentage is 96.41. The total area of this standard normal distribution is 1. So 1 minus this blue colored area of 96.41 leaves us with 3.59. All right. Moving on to the next application. Remember, we could also be asked to calculate the percentage of data points in between two z-scores, or stated graphically, what is the area of the standard normal distribution that lies between two given z-scores. So let's look at an example of this, an extension of the previous problem. The mean score of the students is 60 marks, standard deviation is 10, and we have two students scoring 80 and 50 marks respectively. This is just two random students who have scored 80 and 50 marks respectively. And the question that's being asked of us is what is the percentage of students whose marks lie between these two students? Assume a normal distribution. The procedure is somewhat same. In step 1, we'll look forward to the z-scores for 80 and 50 respectively. So if we look at the z-scores of 80 and 50, so so what you'll notice is that for 50 marks, the z-score is -1 right here. And for 80 marks, let's also look at the z-score of 80 marks. The z-score of 80 marks is given here is 2. So now we know the z-scores for the 50 marks and the 80 marks. What is the next step? Our next step is now to find the corresponding probability numbers from the z-score table. So let's look at -1, the z-score of -1. In this case, we'll use the table towards the left. Remember that the table has been split into two parts. You have the negative and the positive parts of the table. As you can see here, the z-score of -1 is 0.15866. It is 0.15866. What does it mean? What it means is that roughly 15.86 or 87 rather, rounded off, percent of data points lie to the left of -1, which is 15.86. 2.87%. Similarly, the other z-score was 2. 2 for when the score is 80. So if we look at 2 on the z-scores table, and let's see what we arrive at. So for 2 on the z-score table, we see where the value is 0.97725. So let's go here and write it down. So it is 0.97725. Again, what is the interpretation? It means 97.73% roughly of data points lie towards the left of or lie below the z-score of 2 or the marks of 80. Right? So now that we have the 2 percentage points on here, let's understand this. So if you were to look at this graphically, you will see that the -1, the point which is -1 on this, let's just mark it. So the first red colored column here represents -1 z-score, which is nothing but, remember, the first score of the student was 50. The -1 represents 50, right? So the place where you see the red colored column is basically 50 marks. And again, the z-score of 2, that's going to be the second red colored column, the smaller red colored column. This represents 80 marks. The question says, what is the percent of students who have scored in between these two students? So basically, we're interested in this brown colored region that you see on the graph right here. So how do we get that brown colored region? That brown colored region is nothing but this entire area starting from -3 z-score till +2 z-score, this entire area. And from this entire area, we can then subtract this small blue colored area right here, which will leave us with this brown section in between. So how do we get the first area? How do we get the larger area all the way from -3 till 2? This larger area is nothing but the z-score for 2 as seen from the table. So if you take the z-score of 2 and see the value in the table, remember we've written it down. So that number that we got right here, the z-score for 2, the probability that we got from the table is 97.73. And we can just take it here. There we are. So that's your larger area. What is the smaller blue area? The smaller blue area is nothing but the probability of the z-score of -1, which is 15.87. Let's put that here. And then if we were to subtract both of these, we will arrive at the brown colored section, which is 81.86. That's what you see on the diagram above. This is how we arrive at this number of 81.86% marks, or 81.86% of the data distribution of the marks lies between these two. So this is a general principle. Whenever you're asked to find the data distribution between any two given points, all that you have to do is find out the corresponding z-score for both the data points, go to the z-scores table, find the corresponding probability for that z-score in that table, and then when you subtract both of those numbers, you will arrive at the probability or the data distribution that lies in between those two data points. Okay. Extending this concept further, in some cases, you might also be asked to find out all those data points that lie outside of two given data points. Again, by outside, what we mean is those data points that are greater than the higher data point and data points which are lower than the lower data point. If we take a concrete example, it'll probably be easier to understand. So you can see in this case that, again, same question extended further. So you have 100 students at a university, the mean score was 60 marks and the standard deviation was 10 marks. If there are two students who score 80 and 45 marks respectively, what is the percentage of students whose marks are above 80 or lower than 45? Above 80 or lower than 45. What does this mean? What this means is, if you were to look at similar example, for 45, the corresponding z-score is minus 1.5. We can mark it here. So we have the minus 1.5 marked in red right here. And then for 80, the z-score is 2. Okay, so we can simply go here and mark it here. Right, so we have 2 red colored columns. Basically what the question is asking us is, what is the area to the left of the taller left colored column, this section right here, and what is the area to the right of the smaller left color, the smaller red colored column right here. So basically if you add up this area right here and this area right here, then you would have calculated the percentage of data points which are outside of these two numbers. Extending that further, as you can see on the graph of the standard normal distribution for this data distribution on the right hand side, if you add up both of the brown colored sections right here, you will arrive at your answer. So again, using the same logic, if you were to look up minus 1.5 in the z-scores table. So let's go ahead and look at minus 1.5. So our minus 1.5 is 0.6681, as you can see here, 0.6681. Okay, so basically, what does this mean? It means calculate it to percentage. In fact, 0.06681. 0.06681. Yep. So what does this mean in terms of percentage? What it means is 66. It means 6.68% of the data lies to the left of minus 1.5, which is this brown colored section here. Okay. What we also need corresponding to this is this small brown colored section at the end. So how do we get this? The way we can get this is if we calculate the z-score of this point, which is z-score of 2, and then subtract it from 1. 1 is, remember, the area of the entire curve. Then you will get that area which is lying above the z-score of 2. So let's do that. So let's go back and look at the z-score of 2. The z-score of 2 is 0.97725. Let's write that down. Okay. All right. Let's do it again. 0.97725. Okay. So remember, this is this area all the way starting from 2 till minus 3, this larger area. What we need is a small brown colored area, or the brown colored tail towards the end. How do we get that? The way we can get that is we subtract it from the total area. Total area is 1, so you're left with 2.28%. So this small brown colored area is 6.68, and this smaller brown colored area on the right hand edge is 2.28. So if you add up these two, the 6.68% and the 2.28%, or roughly 8.96%, that's our answer. 8.96% of the data lies outside of these two data points of 45 and 80 marks respectively. Graphically or visually, if you see the same thing, it'll be easier. You just have to bear in mind that this point here represents the score of 45. This score here represents the score of 80 marks. And then you can compute these points that lie to the outside. Okay, so I think that is what we'll cover for today as a part of a starting set of applications of the z-scores and the z-score table. In the next video, we'll try and understand the reverse of this, which is which is basically if you are looking at a z-score table. Remember, so far we have been calculating the z-score, looking at the columns and rows that you have here. This is your column, this is your row, and we are trying to find the corresponding probability value. So for example, if your z-score was minus 0.72, then the way we would look up that z-score number is going to be a bit like this. So minus 0.7, which brings us here. Okay, so that will make it more easily visible. And 7.2. So wherever the column and the row intersect, we'll get your z-score of 0.23576. What this means is that 23.56% of the data lies towards the left of the z-score of minus 0.72. So that's what we've been doing so far. In the next video, what we'll be looking at is the reverse. If you are provided with a probability, for instance, if you're provided with a probability of, let's say, 0.7938, what does it mean in terms of a z-score? So we'll be doing the reverse. We'll be looking at the probability and then finding the z-scores, and that again has its own set of applications. So that's what we had for today. Hopefully it was a helpful and instructive video. See you next time.